Uh, I'm a member of the Black Hole Initiative, so that's a group of researchers here at Harvard that study black holes from all sorts of angles. They're physicists, astronomers, philosophers, and we've had conferences where they're musicians and everything all gathered together to study black holes or just about just the topic of black holes. And that's just because if you think about black holes, it can touch just many aspects about science and how people interact with each other, how scientists interact with each other, how science this gets disseminated into scientific knowledge gets disseminated into the public and stuff like that. So it's just like it's sort of a rich topic to study. Um, as a result, there's like not it's kind of hard to give a single presentation on black holes. If you ask someone to do it, they'll probably tell you different things depending on what aspect of black holes they study or what kind of research they do or what kind of scientist they are or like if they're a philosopher or whatever. But I want to talk about black holes from the perspective of the EHT, which is the Event Horizon Telescope. That is this collaboration that I'm a part of, and this is the collaboration that produced the first image of the shadow of a black hole in 2019. Um, so it's just starting here. Does anyone know what a black hole is? First question. Now you don't have to be right, just like anyone want to give a guess.
Anybody can answer.
Yeah, is it Zalika?
Yes, sir.
Yeah, so you want to give a guess or what a black hole is?
A black hole is basically what remains after really big stars, radiation starts to go away after a while when the heavier metals inside of its core turns into iron. And then when that iron builds up, there's no more fusion. That creates radiation. So the core collapses. And since the star is so dense, it turns into a black hole.
Yeah, so that's correct. That what you describe is one of the pathways for which black holes are formed. There are like many pathways actually which black holes are formed, but what you describe that is correct. That is one of the ways that black holes are formed. So the black hole is the thing that's left at the end of that. It's this very compact object with a strong gravitational pull. It's like the most compact object that can exist in the universe. So you'll often see this definition given for a black hole, that the black hole is an object with gravity so strong that not even light can escape. And there's a reason that we say not even. There's a reason that not even is highlighted. And that's because the speed of light is the universal speed limit of it's nothing can go faster than the speed of light in the vacuum. So if you can't go if light can't go fast enough to escape a black hole, and nothing can go faster than light, that means nothing can escape a black hole, right? So a black hole is essentially a point, is like a region of no return. Like if you fall into it, you can't get back out. Uh, and that's the nature of the black hole. So, we took a picture of a black hole. So maybe the first question you might ask is like, if light can't leave the black hole, how do you see a black hole? Like if you can't get the light from it, like when we see an object, we get the light that bounces off the object and comes to our eyes. And if black holes don't give off any of that light, how do we see it? So Dan says that we observe black holes from their interactions with and how they affect the environments around them. So I think someone was asking earlier or said something earlier about like black holes buried in the universe or something like that. That there's theories like that, but one thing that we think is particularly certain is that they're black holes at the center of galaxies. So galaxies form, black holes form along with them, and they follow this growth curve. They sort of grow in tandem. And as the black hole becomes more massive and as stuff gets thrown towards a black hole, it alters the evolution of the galaxy. So the Milky Way has a black hole. We think that it was very active sometime in the past. There are these things called the Fermi bubbles, which we see, which people believe are remnants of the of a period of time when the black hole was active. There exist other galaxies out there like Centaurus A, which have a currently active black hole, and you can see that based off. I don't know if you can see these plumes that are on the um leaving the image like orthogonal to the disk. There are these like plumes of what looks like gas leaving. That's the black hole capturing gas and moving it around and shooting it off into space. And
That's
these
middle, as a middle picture.
There's a middle picture, yeah, that's Centaurus A. That's the center picture. And these plumes are kiloparsecs long. There's like like tens of thousands of light years long. So there's something that needs to be really massive to be able to take all that gas and that plasma and shoot it off tens of thousands of light years off in a distance like that. And there are other galaxies like the one on the right, like ESO 325 GO4, which is an elliptical galaxy. These galaxies tend to have smaller black holes in them. These tend to be young galaxies, and the black holes aren't usually as active as they are as in the Centaurus A. But if essentially the nature of the black hole, like how big it is and how it affects and how the environment gets channeled towards it affects the shape of the galaxy and the way how things are formed within it. So black holes have this relationship with their galaxy, and they kind of evolved um, in hand with their galaxies. Another feature of black holes, another reason why we think they exist is because we see these really bright relativistic jets out in space. So I sort of hinted on that earlier with Centaurus A. What we see is that like if you sometimes you look in space and if you look out there, you'll see these like long lines of just like gas and plasma shooting out like moving at near relativistic speeds, so speeds close to the speed of light. And in order for something to be accelerating matter to that speed, it needs to be something really massive and powerful. And the only thing that we can think of that satisfy that are black holes. So essentially, there's a lot of these smoking gun features that indicate that black holes should exist. Um, but perhaps the most direct evidence of black holes, and I might be biased, is sort of the way how they affect the way how things look around them. And this is essentially what the HT um, tried to do, is that we tried to take a picture of the region around a black hole to see the way how it affects the air around it. So here I have this disk. This disk is showing a JWST deep field image. So the top panel is essentially showing what disk looks like if it's just like there's nothing there. If it's just a disk, it just looks like a flat disk. But if the bottom panel shows what would happen to that disk, so how it would look if I put a black hole in the middle of it. Anyone so there are differences between the two. Does anyone care to like comment on like what those what differences they notice?
What's that?
I was saying like anyone want to point out what differences they notice between the top image and the bottom image. So the top image is like a disk. What the disk looks like if there's no black hole, and the bottom is what it looks like if there is a black hole. Zalika has her hand up again. Oh, actually, let me give David a chance to talk.
Okay, so I wanted to say that the difference in where the black hole is in this disk and where the black hole isn't is that the black hole is sort of bending or distorting the light around it, which sort of makes the disk look like the way it is.
Yeah, yeah, that's exactly right. So you can see the black hole is bending the light around it, and it's causing the back of the disk to bulge upwards, and distorting the way how it looks. And you can actually see the disk bulging below it too. So one of the weird um facts about a black hole, or one of the weird things that it does, is that it allows you to see the image of an object multiple times. Um, so like if you put something behind a black hole, you'll see infinitely many images. I like to think that a black hole is kind of like a funhouse mirror because it warps images in weird ways. But there's a characteristic way in which it warps images. There's a way that from theory that you can predict, like if you work out the math, you can predict exactly the way how you expect a black hole to warp an image. So what that means is that if we see something that looks like this, like the image on the bottom, then that's sort of like direct evidence that we're seeing a black hole because we can predict what that looks like. The most important feature here in this bottom image is this dark feature in the middle. That's what we call the black hole shadow. And that's just because um it kind of is like a shadow. It's like if they shine light behind the black hole, like if light is coming from behind the black hole, the light will fall in and it can't get out. So you just like makes this dark thing on the screen, this dark hole. So that's like a characteristic feature of a black hole.
I heard that you can see behind or what is behind the black hole, safe from in front of it. So like the
Yeah,
light
yeah.
is around from the back, like you can see what is at the back of the black hole.
Yeah, that's true. That's true. That's why the top of this image looks the way it is because the light. So this disc, I put the black hole in the center of the disc, so that would have been behind the black hole, and the light sort of like travels around the black hole, and you see it coming from the top instead of from behind it.
Yeah.
And if anyone is interested in, so I made this little uh I guess web app that you can try. There's a QR code. So it's like filter that shows you what you look like if there's like a black hole like sitting on your like at your camera. And this sort of shows some of the features that I mentioned before. If you lens an object, you'll see like if you were to look at the black hole, you'd see yourself and you'd see like infinitely many images of yourself, and that's essentially what this is showing. This is one of our interns, and we lens a picture of him, and you can see him here. You can see another image of him here, and you can see they're distorted, but you can see all the images popping up and piling up onto the shadow of the black hole. Um, so with that in mind, let's draw some conclusions on how we can observe black holes. So the first thing is that we can observe the effects of black holes on their host galaxies. The second thing is that black holes generate these powerful relativistic jets that punch through galaxies, so we can see those too. That's one of the reasons we know that they're black holes at the center of many galaxies, because we see these jets coming off from the center of many galaxies. And we can observe black holes from the way how they warp the appearance of their environments through a process called gravitational lensing. Okay. So essentially the conclusion is that we can't see black holes, but we can see how they affect the environments around them, like the environments around the black hole. So the one question you might ask is like, why does a black hole have an effect on the environment in this way? In particular, like why maybe it might be like, why does a black hole make things look the way they do when they're there? And I mentioned before that you can essentially calculate how that is done. I'm not going to show you exactly how to calculate, but I'm going to try and give some intuition on why that happens. And it kind of boils down to this concept of gravity. So black holes are a solution to gravity, and essentially what that means is that, so in physics, anyone know what the like fundamental forces in physics are? So there are four of them. If anyone can guess what they are.
There's a weak force, a strong force, electromagnetism, and gravity.
Yeah, so those are the four fundamental forces. So yeah, so gravity is one of those forces. And if y'all do physics, like CSEC or CAPE physics, then the first kind of gravity you learn is what's called Newtonian gravity. And Newtonian gravity essentially works in this realm where like in what we call flat space. And one of the ways how we define flat space is basically, or one of the ways you can tell a space is flat is if you draw a right angle triangle in flat space and you measure the angles of that right angle triangle. They sums to 180, or if you measure the length of the lines and they satisfy Pythagoras' theorem. And if you guys remember Pythagoras' theorem, it just says that you have a right angle triangle and his hypotenuse is of length delta s, and the length of the other sides are of delta y and delta x. Then delta s is equal to the square root of delta x squared plus delta y squared. So that's Pythagoras' theorem. I think you might also see it as like c squared is equal to a squared plus b squared, or various variants of it. But you can just swap the symbols out, just the relationships are all the same. So these aspects sort of define some qualifying factors of Newtonian gravity. So one, space is flat. You satisfy Pythagoras' theorem. The second thing is that time is constant and universal in Newtonian gravity. So that means it doesn't matter where you are or how fast you're moving, people experience time the same way and at the same rate. And the other thing for Newtonian gravity is unimpeded objects travel in straight lines. So what that means is that if there are no forces acting on an object, it just travels at a constant velocity in a straight line. So that's what we learn from Newton. That's what Newtonian gravity tells us. That's what Newtonian physics tells us, and that's what you probably learn in C second K. Now, 100 years ago, like many 100 years ago, since in the past from us, many hundreds of years ago after Newton, Einstein came about, and he sort of rethought physics. He rethought Newtonian physics. He rethought gravity, and a lot of these rules changed. It turns out that a lot of these rules aren't exactly true; they're only approximately true. And essentially, what Einstein realized is that the space is not flat. Like space-time is not flat. Space-time is curved. So here I'm showing some examples of some curved geometries. The most obvious or the most simple curved geometry you can think of is like a ball. If you draw like a big right angle triangle on a ball and try and measure its angles, you'll see that it sums to something greater than 180 degrees. And you'll see that the ball doesn't have straight lines. You can't draw a straight line out of the ball. You have to, if you connect 2 points on a ball, it makes a curve on the surface of that ball. And those curves are often called great circles. So if you want to get from point A to point B on the equator, like if point A is on the equator and point B is also the equator, and you want to get from point A to point B in the shortest distance, then you're best staying on the equator. Like that's the shortest distance because to get to there. And there are other surfaces too. There's things like a Pringle chip. Maybe draw a triangle on that and sum up the angles, they sum up to less than 180 degrees. And the curve, the shortest distance of those are hyperboloids, they're not straight lines. And essentially, so these are sort of like the weird things that happen when you have curved geometry. But essentially what this means for Einstein gravity is that the first thing is that space is not flat, it's curved. Um, So the shortest distances are no longer straight lines, they're curved lines. Angles of triangles come up to weird values, so that the C-sec geometry though is not true anymore. Um, the other thing too is that time is not constant or universal anymore. Time is relative. So if you're sitting somewhere, oh, Giovanni, you have a question?
Now, just saying the Earth is not flat, but the universe is flat.
Yeah. The universe is flat on large scales. Yeah, the Earth is not flat, but the universe is flat. The universe is flat on large scales. So if you ask the question on different scales, then there's like small curvature. But if you just look on large scales, it's flat. So it sort of depends on how you frame the question. But what time being relative, what that means is that if you're sitting in the universe, then depending on where you are and how fast you're going, you will measure time moving faster than someone else or slower than someone else. Like two people, their clocks will tick at different speeds, and they'll experience events occurring at different rates from each other. And the last thing is that unimpeded objects travel on curved lines instead of straight lines. So that intuition matches what we saw before with the ball and with the Pringle chip. So a nice example that I like to give of this last thing, that um, shortest distances travel on straight lines, is with planes. So imagine you run an airline, right? And you're trying to make a profit. So and there's basically nothing in the air. So if you're trying to get people from point A to point B and you're trying to be as efficient as possible, it makes sense that you go from point A to point B in the shortest distance possible, right? The thing that will get you from point A to point B in the shortest time amount of and use the shortest amount of fuel. So you want to get there in the shortest distance. So there's this website that shows you the live plane traffic. That's what this QR code shows. And you can just see planes that are flying around, see where they're going, see where they've been, get flight history and stuff like that. And one question you might ask is suppose you take a plane that starts in San Francisco, so that's in California in the US, and is going to the other side of the planet, so that's Dubai. So you want to see what path a plane going from San Francisco to Dubai takes. And your intuition from Newtonian physics is probably that, you know, if you want to take the shortest distance, you're traveling a straight line. So you're probably expecting to take a path along this like red dash line, right? But you know, on this website you can look on the flight history. So I took a plane that went from San Francisco to Dubai and looked at that flight history to see what path it took, and I got something that looked like this. It's this purple line here. So anyone knows what's happening with this purple line? Anyone know why it's knows why it's sort of shaped the way it is? Can you take a guess?
Nathan, you want to answer?
What was that? Why? Which lines of circle? The path of the plane?
It's what?
Wait, could you repeat the question?
So I was saying that if you're going from San Francisco to Dubai, you might
Right.
expect that you're traveling a straight line, like across the
Right.
Pacific, from
Mhm.
San Francisco to Dubai. But if you see the path that the planes actually travel is along this purple line. So do you know why? Can you know? Do you know? You care to take a guess of why they travel along the purple line and not the red line that I showed earlier?
Sea monsters. I joke. I joke. I think I remember seeing the explanation. I don't remember if it was that they're trying. Is it have to do with the jet stream, or is it more efficient to travel the longer route, or just because the globe we're looking at is a flat projection of a curved sphere or
So
something
it,
along
it's
those
it's the
lines?
last one. So it's because
Right.
this, yeah. So it's because this sphere is curved,
Yeah.
and
Right.
this is a flat projection of the curved sphere. So like, because
Right.
you know the flat projection is like a flat thing, and it's not very easy to map a curved thing onto a flat thing, so it sort of distorts the lines. So if you were to actually look at what these paths look like on the Earth, you'd see that they just look like essentially straight curves on the Earth, like just like lines, essentially like what the lines along longitude and latitude look like on the Earth. They're just like, they're not really straight because you know they kind of wrap around the Earth. They're like curves on the Earth, but you see they're basically these great circles on the Earth, or segments of these great circles on the Earth. So what's actually happening is that the plane is flying from San Francisco to the North Pole and then down to Dubai.
Oh, and there's an interesting thing. I remember watching in a YouTube video the other day, and they were saying that because of the curvature of the earth, basically the time zones, Neil was explaining it. He was saying that the time zones are actually the distance between each time zone mathematically is shorter when you're flying closer to the poles. So if you fly along that path, it would take you a shorter time than if you're supposed to go directly, like fly in a straight line.
Um, that is it is related. It's not quite that, but it is related. But yeah. What you're saying is true. That if you fly around the pole, then you go through the time zones faster because they're closer together up there. Um, okay, so now that we have this intuition on oh there's should I there's someone in Lloyd Gordon, should I let them in, or
I'll let them in.
yeah, so now that we have this intuition that you know when geometry is curved, it affects the path that things travel. The first one thing you might want to do is like, you know, test to see if this is really true. Like if there's a massive object, so essentially gravity is the force between massive objects. So if you put a massive object at somewhere, does it cause light to curve around it? And one of the first tests of general relativity, or a lot of the first tests of general relativity actually were these solar system tests. And if you want to test general relativity, you want a really massive object. So like, you know, what's the most massive object in our solar system?
Who will answer that?
Is it the sun?
Yeah, it's the sun. Exactly. So you want to test general relativity by using the most massive object in the solar system. So you're going to use the sun. So what you want to do, if in this test is essentially say you want to look at something when the sun isn't there, see where it appears in the sky, and then put the sun there and see how its appearance changes. But of course, like, you know, if you ever look at something in the sky, the sun is there, you can't really see much because the sun is very bright. Like you can't see stars or anything when the sun is there. So you need to somehow like have the sun there, but not have it be bright. So like, how do you do that? Anyone have any idea?
Sean can tell you. So
Like how can you have the sun being in the sky but not have it be bright?
Eclipse, I guess.
Yeah, the eclipse, exactly. So one of the first tests of general relativity was with an eclipse. And they actually do this test a lot every time there's an eclipse. There's an eclipse every 2 years or so. So the people rerun this experiment. But one of the first I think it was the first experiment for general relativity, was the gravitational lensing of stars in the presence of an eclipse. So the idea is that there's this guy, this Englishman, Arthur Eddington. Like Einstein makes this prediction in 1916. Arthur Eddington reads the paper, and in 1919 he goes on this expedition to take pictures of the sky. So he essentially takes pictures of the sky at night when there's no sun. So you see where the stars are in the sky, and you just wait until the sun gets there, and then you take the picture again. And if general relativity is right, then the light will, because the sun is there, instead of the light traveling in a straight line from the star to you, it travels in a curved line, and that means that you see the star at a different location, because the light is sort of coming at you at a different angle because it's curved. Um, so this is what our Eddington did, and this image right here is showing the two images laid on top of each other. So the image of the sky when the sun is not there, and the image of the sky when the sun is there, and you can essentially see that the stars are displaced. So you can see that the presence of the sun has displaced the way how the stars look. So you can see that the sun is actually bending the light that's traveling from the stars to the earth.
displace them that much?
Yeah, it's a relate. So
Gonna be a very tiny thing.
yeah, I mean, like it's kind of
Sheesh.
interesting because they didn't have that much advanced technology in the 1990s. So you have to do an experiment where it's kind of unambiguous what's happening.
People wouldn't even notice this until they actually try it out for themselves.
Yeah,
Honestly.
it's really interesting because like it's a thing that happens all the time, but unless you actually like try and look for it, you don't notice it exactly. They redo this experiment all the time. There's an eclipse in 2024. So they had a bunch of people do the experiment, so they're currently collating that data, and you'll probably hear, if you look it up in a couple months, you might hear results on what they say. Usually the experiment agrees with general relativity, but I think about science is that you always have to do experiments to test to see if things are correct and the predictions are correct. So they usually redo the experiment. But yeah, this was a success for general relativity prediction. Space-time is curved. You can it's weird effects. I could maybe I could come back one day and talk about general relativity, but there are all sorts of weird effects in general relativity. But
Yeah.
this was one of the first tests, and we know it's correct because of that. Sorry, did you have a question?
I was saying, please do that. Come back and talk about general relativity.
Yeah. So all right. So I'm going to start going into essentially the EHT targets. So the EHT I mentioned before is like the telescope's a collaboration I'm a part of, and there are two main targets that the EHT was trying to observe. One of them is the black hole at the center of the galaxy M87, and the other one is the black hole at the center of our galaxy, Sagittarius A star. And so I'm going to talk about the prior evidence for these. So why we think they're black holes essentially at the center of these galaxies. So first, I'm going to start with M87. So we have many years of observation of M87 at many wavelengths. So they're light is a set of wavelengths in the electromagnetic spectrum, but there are many other wavelengths in electromagnetic spectrum, like radio waves that you hear that sends you a signal on your radio is an electromagnetic spectrum. That's at a larger wavelength than light. Wi-Fi is also in the electromagnetic spectrum, UV radiation from the sun, and so on. And if you observe things at different wavelengths, you can see different length scale structure from those objects. So we've looked at M87. This image that I showed you on left is the Hubble image of M87. But M87, you can actually, I'd be curious. I've actually wanted to do this. I've never been able to do this, unfortunately. But supposedly you can take a normal optical telescope and see this jet from M87, because M87 was discovered by Messier in in the 1700s, and he just had an optical telescope, and like he was able to see this wisp. So I think supposedly you can just like you can see this with amateur astronomy. I think it's kind of hard to do, but it's possible. I'd be oh yeah, Giovanni, you have a question?
Now, where on this is M80? Oh, was on the left?
Yeah. So what I'm saying is that on the left is like an optical image of is what M87 looks like when taken from the Hubble Space Telescope. But historically, M87 was discovered in the 1700s, and during that period of time, it was all they had were optical telescopes, and they had small optical telescopes. So I think it's supposedly you can just like go out with like a relatively small optical
They didn't
telescope and
have
see
light
it.
pollution then.
Yeah, I guess like the light pollution probably makes it hard, but supposedly you can see it. But I mean, apart from that, we've observed M87 at different wavelengths. We observed it with X-rays, with ultraviolet rays, and we observe it with the radio wavelengths. And really, with the radio wavelengths, you can start to peer in very deep into that galaxy. And it is with radio wavelengths that the HT did their observations and took the first image of the black hole shadow. So more on that later. The other source of interest for the EHT is Sagittarius A star. This has its own history. It's not as old as the history of M87, but interesting history nonetheless. So the evidence for this is a bit different, or the evidence for this prior to the HT observation is a bit different. If you look deep into Sagittarius A star, so remember this is like the black hole at the center of our galaxy. You'll see this like stellar cluster. This is like an unresolved stellar image, X-ray image of that stellar cluster. There was this group at UCLA, the Keck group, that looked at this cluster with a high resolution telescope, and we were like looking at stars orbiting in this cluster. So each one of these like bright dots, not really dots, but like blobs are stars at M87, and they took pictures every year, and they stitched it into a time lapse. So these stars are huge, by the way. They're like 10 times bigger than our sun. So they're really, really big. And the sun doesn't really move much in a year because it's really massive. The bigger an object is, the slower it moves. So if you see the object being moved really fast, you need a lot of force in order to get it to move really fast, especially if you want it to accelerate a move in a circle. So if you look, it went from looking at these stars, I think this is 10 years or something of footage, you can see the stars just like moving around. Like they're being whipped around. So you have these objects, these things that are 10 times the mass of the sun, moving at like half the speed of light.
That's a
In
lot.
particular, there's a star S2 that's moving really, really fast. Sorry, do you have a question?
I'm saying that's a lot of energy to do that.
Yeah, it's a lot of energy, exactly. You need a lot of energy in order to get these things to move around. Like you see, um, this is a showing the trajectory of these, but you can see that you can model the trajectories of these stars with actually Newtonian gravity, just because they're sufficiently far away that you can accurately describe them with Newtonian gravity, and you can see that the Newtonian gravity predictions really well match the trajectories of the stars. A common fact about Newtonian gravity is that the trajectories are what are called conic sections. So they're either hyperbolas, they're either parabolas or ellipses. And a circle is just a special case of an ellipse. So you can see that all of the trajectories satisfy those criteria. And in particular, you can measure all these trajectories, and they're all orbiting a single object. And you can calculate the mass of this object if you just use Newtonian physics, GMM over R squared. And what you find is that you get an object that is 4 million times more massive than the sun. And be in mind, this is an object that like you can't see in the video. Like when you look at the video, they're orbiting something 4 million times more massive than the sun, but you can't see something that's invisible that they're orbiting. Yeah.
So you can model them and basically ignore their interactions with each other because
Yeah.
more massive than them.
You can ignore them interactions with each other because the plot doesn't make it very obvious, but they're actually really far from each other. So they effectively don't feel each other. But so because they're really, really far from each other, in order for them to even be feeling that central thing, it has to be really massive. Like these things are like kiloparsecs away from that central thing. Or actually not kiloparsecs, just parsecs, but they're very far away from that central thing. So that central thing is essentially Sagittarius A star, that's the black hole at the center of our galaxy. That's the Milky Way Galaxy. It's 4 million times more massive than the sun. So that's 1,000 thousands the mass of the sun. The sun's already really massive. It's kind of hard to understand the scale of these things. Like it's hard even for me to understand the scale of these things. Like the Earth is really like the Earth is big. You can fit the Earth and the entire solar system in the sun and have many space left over. And on top of that, you can fit, the sun, the Sagittarius A star is like 1,000 of those. So you can fit like 1,000 like a million suns in that. So it's huge. It's very, very, very much massive. But it's also very far away. It's like 27,000 light years away. So it takes light 27,000 years to travel from Sagittarius A star to us. And the reason for that is just, the universe is really big, the galaxy is really big. It just takes a long time to get from point A to point B because of just how big things are. And the other black hole that we're talking about is M87. This was the one that I said you can observe with the jet at least with optical astronomy. This is actually one of the biggest black holes that's ever been discovered. It's 1,000 times even bigger than Sagittarius A stars. It's 1 billion times the mass of the sun, and it's also 1,000 times farther away. So it's 55 million light years away. So if it's that much bigger than Sagittarius A star, you can imagine that it's a it's like Sagittarius A star is already a massive black hole. So 87 is an even bigger black hole, and but they appear roughly the same distance to the sky because of length mass relationship. But if you were to put M87 beside Sagittarius A star, you'd see how big it is. And this video is just showing you that. So if you took M87 and just like brought it closer to you, this just shows you how big it would appear on the screen. So you can see that it's massive. Okay. So again, I'm gonna talk more about scale of things. What? Yeah, sorry, I was reading the chat. So I'm gonna talk more about the scale of things. Um, this is M87. This is the picture that we took. Uh, just for reference, if you were to put, say, the solar system M87, it would fit very, very neatly within the shadow. So like, the shadow, just the shadow alone is huge. Voyager 1 is like the farthest satellite we've ever sent out. It's gone beyond our solar system. And even that just reaches the edge of the shadow. So M87, like just the size of it, the sheer size of it is huge. Anyone ever seen Interstellar?
No, I haven't seen that one.
Yes, I've seen that one.
Well, yeah, even for just so what Interstellar is like is this movie that's a kind of the black hole is sort of like a central character in Interstellar. There's this massive black hole there that they call Gargantua, and in Interstellar there's a lot of like weird general relativity, weird physics effects happening. A lot of it is accurate. A lot of those effects are actually calculated by Kip Thorne, a Nobel Prize winning scientist, very famous black hole researcher. Um, but yeah, there's this black hole in interstellar called Gargantua. It's supposed to be very massive, and M87 is actually 70 times bigger than Gargantua. So this real, they say reality is stranger than fiction. Sometimes there's an example of it. This black hole that we have that we looked at is even bigger than the black hole that they like imagined up for that movie. So M87 is huge. But it's also really, really far away. So like the thing is that like you clearly don't see it in the sky with your eyes because it's really, really far away. But we know how far away it is, so we can like calculate roughly the size of the telescope we need in order to see M87. So the way to think about it is like imagine the telescope is like a camera. Like if you want to take a picture of something that's really, really far away, it looks really tiny, or something that's really small in your field of view. To take a picture with a camera, you need a bigger camera. Like the bigger camera is like the more resolution you can get, so the more you can zoom in, right? So we need something similar to take a picture of the black hole. Like we need a really, really big camera so we can zoom in really close so we can see the black hole. So Sagittarius A star and M87 are roughly the same size. So I'll talk about Sagittarius A star first. Anyone care to take a guess of how big of a camera you need to take a picture of Sagittarius A star? Yeah, David?
I'm gonna make a guess. I'm gonna say as big as a house. I'm just gonna say, I think a big as the Earth would be too much. So I think a big as a house. That's my opinion.
Anyone else want to guess?
I said B as well.
All right. So who said car? How many people said car? No one said car. We have two people say house. Anyone else say house? Anyone say city? And
We
anyone's oh, we have one person for city.
aren't we already hand? I mean, I'll let him answer.
And who said earth? So no one said earth. Oh, one person said earth.
Earth.
So two people say earth. So that so the answer is actually the earth. You need a camera the size of the earth if you want to take a picture of those two black holes. And
Wow.
so, obviously we don't have a camera the size of the Earth, but let me explain how you can get to that result. So it's actually, you can sort of like do a back of the envelope calculation to get that result. So, if you think general relativity is correct, then general relativity tells you an expected size for the shadow of the black hole. It tells you that it's something like root 27 times the mass times Newton's constant divided by the speed of light squared. Ignore this r. This r is the distance to the hole. So we know how far away Sagittarius A star is. It's 81 kiloparsecs. So that r is like 81 kiloparsecs. And we know the mass. We know the mass from Andrea Gheze's observation that I mentioned before. So it's for um, solar masses. We know what Newton's constant is. You can Google that. We know what the speed of light is. So like if you plug all those in, you get the angular diameter of 52 microarcseconds. So that's just like how big it looks like on the screen, or how big it would look in your field of view if you were to look at that. And again, like these numbers kind of don't mean anything unless you have a point of reference. So what that is equivalent of is that you need the resolution to take a picture of a grapefruit on the moon. So like you're standing on Earth and you take a picture of the moon and you need to zoom in enough to be able to see a grapefruit sitting on the moon. So that's the kind of resolution we need. So like knowing that we need that resolution, you can calculate what size camera you need in order to get that. And there's this thing called the Rayleigh criterion, which allows you to do that. It's if you have a circular aperture, this is an approximation, not exact, but it's a good approximation. If you have a circular aperture, then theta is the size of your camera, and the size of your camera is equal to 1.22 times the wavelength that we're observing at, divided by the the size of the source, right? So the EHT, the Event Horizon Telescope, observes in radio wavelengths. It's like a millimeter wavelength, roughly. We already calculated the size of the source. It's 52 microarcseconds in diameter, so roughly 20 microarcseconds in radius. Really 25, but roughly 20 microarcseconds in radius. And then we know and then what that tells us, if we plug those numbers in, we get a diameter of 11,000 kilometers. That tells us how big the camera has to be, and the diameter of the Earth is 12,000 kilometers. So we roughly need something the size of the Earth in order to take a picture of these black holes. Right? I don't know about you, but I don't have a Earth-sized camera sitting around. So how do we do this? How do we take a picture of the black hole given that we need an Earth-sized camera? Well, we use a technique called VLBI. So we don't have a single telescope the size of the Earth, but what we do is that we have many telescopes that are sitting at different points around the Earth. So what you can sort of think of it is that each pair of telescope is kind of like a pixel, and essentially what we do is that we can't cover the Earth in telescopes to make a full camera, but what we can do is that we can just have sort of like an incomplete camera with pixels that are sort of sparsely spaced around the Earth, and then we can stitch the information from the pixels together in order to construct an image. Um, so That is essentially what the Event Horizon Telescope is. It's this network of radio telescopes that all just essentially once a year we point and look at the same point of the sky, record the information, and then we correlate that information and produce an image. The EHT is a collaboration. We have more than 300 members from all around the world, representing I think all of the continents, like technically even Antarctica, just because we have a site in Antarctica. That's the South Pole Telescope. As of 2024, we have 11 sites. We and every single observation, so we usually observe for 1 week every year, and a single observation will generate petabytes of data. So again, it's sort of hard to understand these numbers. So, in a more intuitive description of this, that we store this data on hard drives, and a single observation ends up generating like half a ton of hard drives. So it's like a lot of data. And it's so much data that we can't send it over the internet. So we actually have to fly the hard drives from sites from different sites that are correlated so we can analyze the data. There's just too much data to send over the internet. So our data bandwidth is essentially determined by the airspeed travel. This is just a picture of some of our members from the the collaboration meeting last year. This was in Taiwan. This is this is to show that we're kind of a diverse group. There's a lot of us from all over. They have a local Jamaican there, so I'm there too. And we all work together for a single goal. Okay, so now back to this camera analogy. So I mentioned the way how I describe the telescope earlier is as a camera, but as said before that we don't have the full Earth is not covered in the camera. So you can think of the Earth essentially like it's a camera sensor, like a digital camera sensor. And each telescope is like a pixel on the camera. So essentially we have like a camera sensor where most of the pixels are dead. We only have like some pixels working. So like how do we take a picture if most of the pixels are dead? Uh, there are two ways that we do it. One is through this technique that called VLBI, which I'll discuss a little bit, and another one is through this technique called Earth aperture synthesis, which I'll discuss after. But first, I'll talk about VLBI. Um, so it, in 2017, we only had 8 sites, and we produced this image. So how do we produce this image with 8 sites? We do it with VLBI, and essentially what VLBI is doing is that anyone here play music? Anyone play an instrument? Oh, David, what you play?
I play the keyboard. The piano.
So you when you play the keyboard, do you read sheet music when you play the keyboard?
Sometimes I'm not the best at it, but sometimes I do.
Yeah, and with the sheet music, essentially, what it's doing is that it tells you like what note to play and for how long, right, and when to play it, right?
Yes, exactly that.
Yeah. So the thing is that when we observe an image, we're kind of what we're observing essentially is kind of like we see the sheet music, like we see some of the notes of the sheet music, but we don't hear the full song. So normally when you hear music, you hear the full song, and then from the song you sort of transcribe that to sheet music. What the EHT is doing is it's as if it's seeing like pieces of the sheet music, and then we have to like guess the song after seeing pieces of the sheet music. That's kind of what we're doing, and this is actually related to a lot of the compression algorithms that are in use on the internet. So in particular, like the MPEG compression algorithm, is sort of doing sort of a similar thing where it takes an image and it does what's called a Fourier transform, and it gets like the image frequencies, like the image notes of that of anything that you see, and then it sort of does transformation on those image frequencies. So whenever the EHT is observing, we don't see the image on the left. We see pieces of the frequencies on the right, like pieces of those image notes, sorts of things. Um, and if anyone have any questions, like don't be afraid to interrupt if you some if you have something to ask. To kind of get intuition on what this is like, there's this. So this is like an analogy my advisor came up with. Is like imagine like you're looking at a pond and there's some ducks in the pond and you're just looking at the water, like the water beating up and down on the side of the pond. and you want to know the position of the ducks in the pond and how many ducks are in the pond, just by looking at the water beating up and down. So when we're doing VLB, it's kind of similar to this problem. So I'm going to talk about two sort of scenarios. One in which we have some ducks and they're really close together, and another scenario where you have some ducks and they're very far together. So in the first scenario of the ducks and they're very close together, they kind of, they wad their feet, they beat up and down, and this generates wave fronts, and those wave fronts like propagate out to the side to the exterior of the pond, and we observe those wave fronts. And they look a certain wave. They make waves of certain amplitude and certain wavelength.
I
Now,
believe
when the
David,
ducks are,
question.
sorry, what?
David has a question.
Yeah, David, you have a question?
Yes, I wanted to ask just for a quick moment, moving to where you were talking about black holes. How did scientists figure out that black holes really have this immense gravity and they take in all of these things and that light can't escape it? I was just asking, how did they figure out that this is what black holes actually do when they're so far away from them?
But I'm gonna answer that briefly, and I can answer it more at the end. But the black holes are kind of weird in science in the sense that, so typically what happens in science is that you sort of observe a weird phenomena, and like you don't you have data on it but you don't know why it happens, and then some theorist comes by later and sort of gives an explanation for why it happens, and in the process of giving an explanation they make a prediction, and they do an experiment to verify the explanation by seeing if the prediction matches your experiment. Black holes are different in the sense that the black holes were a prediction. Essentially, like Einstein came up with general relativity, and general relativity was used to explain this thing called the perihelion shift of Mercury. And then one of the first predictions from general relativity, as I mentioned before, was gravitational lensing. But sometime shortly after Einstein came up with general relativity, someone also predicted the existence of black holes. And because it's a solution to general relativity, you can just like, do the math and see what should happen, like what sort of properties and effects they should have. And then it becomes a question of like, do these things actually exist in nature or not? Like, that you can mathematically work out their properties. Do they exist in nature or not? And it was only like maybe 50 or 60 years ago did they actually start observing black holes in nature, just because they're very far away and hard to see. Hopefully that answered the question.
Yes, I understood better now. Thanks.
Yeah. Yeah, so this duck thing. So essentially like this question is like you want to know how many ducks are in the water based on the wavelength of the water on the edge of the of the pond. And you have two scenarios, one on the left where the ducks are really far away and one on the right where the ducks are really close together. Anyone see any difference between the wave patterns on the left versus the right?
The one on the left is more uniform in terms of like the distance between the wavelengths, between each wavelength, whereas the one on the right has more different distinct successive peaks of like where one crest is higher and then,
Yeah, exactly. So what happened is that uh so there's this sort of this thing, this weird feature of Fourier transforms, which is that small scale features, so essentially like if the dots are really close together, correspond to long wavelengths. So what this means is that the wavelength associated with the wavefronts that reach the edge of the pond are really long. So you can see they sort of undulate very gently because the wavelengths are really long. And then that means the opposite happens when the ducts are really far apart. So on the right, the ducts were really far apart, and that means the wavelengths are really short. So it looks more chaotic because there's more structure there that you can fit into a smaller space. So this is essentially what's happening with VLBI, like large scale features in Fourier space corresponds to small scale features in image space and vice versa. So the reason I mentioned before that image algorithms or compression algorithms on the internet take advantage of this, and that's because when you do the Fourier transform, essentially what that means is that all the small scale features in the image get put to like large distances in the Fourier space, and you can just like essentially crop them out. And when you do the inverse Fourier transform, you sort of get an image that looks roughly the same, but while storing much less information. Anyway, this sort of technique is it was employed by Martin Ryle in 1974, for which he won a Nobel Prize. And this is essentially what VLBI is. So instead of us looking, sitting at the edge of a pond trying to count ducks, what you have is that you have telescopes sitting on the Earth trying to look at a black hole, and telescopes that are really, really far apart measure long wavelength structures, so that looks see the small scale features of the black hole, and telescopes that are really, really close together measure large scale features, so that it sees the large scale features around the black hole. So back to the AHT. Essentially, if you take the telescopes that we had during those observational campaigns, you can draw lines between them, and these form the baselines of the wavelengths that we observe. So I had a demo here to sort of drive the second point across, but I don't think the audio from the demo is working, unfortunately. I don't know. Can you guys hear it?
No.
No.
Yeah, okay. So the demo is, so what this was to show is that what was happening is that I was going to play a song, and I mentioned before there's this analogy between music and what's happening with music and sheet music and the images that we observe. And the point I was going to make is that you don't really need all the notes in a song in order to identify the song. So what I was going to do is that I was going to sort of just play a song, but add just like one note at a time, and you'd be able to tell me when you'd be able to recognize what song is playing. And what you'd be able to see is that you can actually recognize a song with a limited number of notes. Like you don't need a full set of notes in order to recognize the song. You can usually just strip down the song to like sort of a simple thing. And that's essentially the case with the telescope. You don't really need every pixel in your camera to take a picture of something. You just need like enough pixels basically in order to take pictures of something. That's how VLBI works. The second thing that we do in order to be able to take a picture of the black hole is this thing called Earth aperture synthesis. So what that means is that essentially um, the object that we look at, M87, for example, is really, really static. So like if you have a camera and only some pixels are working, but the object is static, essentially what you could do is that you could just move where the pixels are. So like you can like say take a picture initially at one point in time with their 10 pixels that are working. And because the object is not moving, you just like stay still and rotate the camera and take another picture, and then rotate the camera again, take another picture, and just like stitch the pixel information from each rotation together. You can generate the image.
Kind of like how CRT monitors work in reverse.
Yeah.
where
Yeah,
you
exactly.
go-
Yeah, because the CRT has a line, so it just stitches the picture up together piece by piece. So it is
Yeah.
kind of like that. And that's essentially what we do with the EHT. So the thing is that the telescopes sit on the Earth, and the Earth is rotating. So like if you have two telescopes that form a baseline, and that baseline corresponds to a point in Fourier space, and over time the Earth spins. So like if we just stare at the object as the Earth spins, it generates more points in Fourier space. So it is very much similar to a CRT TV. So this is just like a simulation that's kind of showing that effect. Like as the Earth spins, we pick up more points in Fourier space, so we're able to like have more effectively more pixels to take a picture of the black hole that we look at. So that's what I have for today. I sort of trying to explain how we took loosely how we took a picture of that image, and how the science behind the technique that we use work. Um, Hopefully it was interesting. If you have any questions, please throw them at me. I can answer any questions you have.
Questions, anybody?
Thanks for your presentation, Dominic. Very interesting, man. What I learned was about definitely the addition to my knowledge on this thing was the use of Fourier space. I didn't know that. And reflecting on it's a very smart approach to a very difficult challenge, that proved successful in the end. I'm just curious, what particular role did you play? Were you helping to crunch the numbers, or if you could elaborate on that a little bit? Thanks.
Yeah, so I'm a theory. So yeah, that's a good question. So astronomy, it used to be in astronomy that you'd have like 2 or 3 scientists that did everything. But especially nowadays, like a lot of scientific collaborations are just very massive. like the EHC has 300 members, so then tasks become more specialized. So as a result, you don't have you still have some people that do everything, but you also have people whose roles are more specialized. So I'm more on the theory side, so I'm more on the number crunching side. What happens is that, the telescope does observation. You have instrumentalists that kind of make sure the telescope is pointing the right way, they wire up the electronics in the correct way, make sure that the data is being collected. And then you have people who correlate the data in order to get what we call fringes. That's just essentially yeah, the data from each telescope. You sort of get them and you need to line them up. You need to line up the data, but because the telescopes are observing at the same time, but they don't they're not immediate. The signals from each telescope are not immediately connected together. So there's someone whose job is to get the signals and align them. And then after that, after you get the aligned data, you give those to the theorists, and then they do theory interpretation. So they try and like make measurements to try and like understand what they're looking at, transform images, and I'm on that end. I'm doing the theory interpretation. So I develop models and a lot of mathematical models to explain the data that we see.
Thank you. Very nice. Yeah, man.
Yeah.
Any more questions, Dominic?
Yes,
That
one,
article, yeah.
one question. I'm still trying to wrap my mind around. It was very interesting. Thank you very much. I learned a lot. But there's one thing in terms of the final picture regarding how you explained how the camera takes the picture. How accurate would you say the final thing is 100% accurate? Is there any marginal error between the result that you get and what the true image would be?
Yeah, so I mentioned that's a really good question. So the thing is, we only have some pixels, right? And I mean we have various techniques and tricks in order to fill in the pixels that we don't have. But at the end of the day, we don't fill up the full screen, but yet we have a picture that is filling up the full screen. So like what is going on? The answer is we use essentially algorithm. There are certain things about the image that we know has to be true. Like for example, we know the image has to be compact. Because the M87, we don't see it. We don't just look out in the sky and see M87 all over the sky. It's compact. It takes up a small amount of space. So and we know that the 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 image needs to be we know that the image needs to be fairly regular. We know how bright it needs to be because you can kind of just like shine you can point a single telescope at M87, just measure how many photons you get, and that tells you how bright it needs to be. And those rules give you extra constraints. And with those extra constraints, you can sort of generate probabilistic structure that the image has to satisfy in order for those constraints to be true. And what that means is that at the end of the day, you just get like a lot of images. You get like a whole family like of images. You get like millions of images, and they all are slightly different. And so what that means is that there are certain features that we are not sure about, but that will be different from image to image. But then on the other hand, that also means there's certain features that we would be sure about because they'll be the same amongst every image. And one thing that we are sure about is the fact that you have this deep depression here in the middle. I mentioned before that one of the smoking guns from black holes that you have this like black, the black hole is black, you don't see it. And like all the images have this feature here. If it was a star, you wouldn't be black in the middle, you see a star. So essentially the answer to that is that there's certain things that we're uncertain about, but there are also certain things we are certain about. And one of the things is this dark depression.
Okay, thanks for that.
And as you have the image on the screen now, could you describe why certain parts are brighter and darker? I see there's a bright flare. I know the reason, but if you could explain to everybody, that'd be nice to let them better understand why it appears as it does.
Yeah, so I mentioned before that you can't really see the black hole, you only see the stuff around it. So really what you're seeing here is a plasma. So the black hole has what's called an accretion disk. Accrete just means it sort of swallows up stuff. And the disk is made out of hot plasma, like 10 to the 11. So like what was that? Like the trillions, like more than trillions actually. That's like I actually don't know what's bigger than a trillion. but trillion is like 10 to the yeah, it's not anyway, it's very hot. It's like 10 to 11, 10 to the 12 kelvins. Hot. So it's moving very fast. And it's also moving around the black hole. And one of the effects of relativity is this thing called relativistic beaming. So whenever things um move really fast, they sort of beam light in the direction that they're moving. So what that means is that if the gas at the bottom of the black hole is essentially like coming towards us, so it's beaming light towards us, and that's why it appears brighter. And we believe that that is essentially tied to the spin of the black hole, because the black hole's space-time is like dragging the gas around it, and we're seeing that being beamed towards us.
And just to be clear for everyone, that is an understood thing, that, you know, nothing falls straight in, but it actually spins around again in the accretion disk before eventually passing through the event horizon.
Yeah, that is true. So it's not like plunging into the black hole. It's sort of like orbiting the black hole, um and the black holes are dragging it around. So this stuff is not necessarily falling into the black hole. Like if it were to fall in the black hole, we wouldn't see it. Yes, Javon.
I believe I read somewhere once where they mentioned that the black hole could be like the most efficient energy generation device theoretically. Like if you
Oh
were
yeah.
to generate energy using a black hole, it'd be like 40%, or so I remember something like that. You're familiar with that?
Yeah, so there's this very famous process called the Penrose process, which is a process for energy extraction around black holes. I think I mentioned before that one of the smoking guns for black holes are these relativistic jets, like kind of like this. And this is, I mentioned, like you need something with a lot of energy in order to like produce these jets. So the thing is that like it's kind of this was kind of hard for me to wrap my mind around initially, actually, because it's like, you know, the black holes are this thing where things like to fall in, and when they fall in they can't escape. So how is it like shooting off gas that we can see? And the answer is essentially what you're describing, this energy extraction process. So what happens is that if gas is sort of living in some region around the black hole but doesn't quite fall in, it can interact with things in such a way that it ends up leaving that region with more energy than it had initially. And that essentially like extracts energy out of the black hole. It's sort of this weird non-local kind of thing that happens. But it
It's
extracts like
kind of like
it extracts a lot of energy, and then that energy gets shot out. So you end up with these relativistic jets where they're shooting particles out near the speed of light.
like how they got Voyager to steal energy to go around the planets.
Yeah, it's actually it's something kind of similar to that.
What they call it? I don't know what they call it for that process.
I think they call it gravitational. I could be wrong about this, but I think
Slingshot
they call
or
it like a
something like that.
gravitational slingshot or
It's a
something like that.
slingshot. Yeah.
It's
So
something kind of similar to that.
So
But
there are
it's
some
not.
sci-fi book where like some advanced type 2 or type 3 civilization, they would just have black holes and then I guess put them in some sort of structure and then extract energy from them and use them to power their civilizations.
Yeah, like I mean, maybe if there was technology, like if they have the technology to do something like that. There has been like, you know, one of the things that's kind of unfortunate about uh black hole, or make not really unfortunate, but make black holes kind of hard, is that we can't create them in the lab. Like they're just kind of hard to. We can't create them, so they're just in the universe, so we just have to kind of
You
look for
could
them.
in the LHC, some about like a Kugel Blitz. A Kugel Blitz. You know
Oh,
what you know what to talk
not sure.
like a very small, very, very tiny black hole. Called a
Okay.
Kugel. I think it was a Kugel Blitz. Let me check. But you can continue asking other people questions.
I was curious, as a very massive gravitational object, Have you looked into any of the information or the studies on dark matter halos around massive objects like supermassive black holes?
Yeah, that's a good question. So I'm not that plugged into the dark matter community. I'm sort of like aware of theories that exist out there just because it kind of touches on the kind of stuff I study, but I haven't studied them directly. Well, I can tell you that, I mean, I just know like some basic facts about dark matter. I know that if it you know it's sort of kind of similar to black holes in the sense that we don't see it. Like it's matter that we don't see, so we call it dark matter or acts like matter. I mean, like it's we see something that acts like matter and it's dark, so we call it dark matter. Different galaxies have a different amount of it, and it tends to clump together, so it acts gravitationally, and it also tends to clump around supermassive black holes. And people have all sorts of different theories for what dark matter is, and depending on what dark matter is, it interacts with the black hole in different ways. So, like, one common thing that you hear people throw on a lot is that dark matter is axions. I don't know if anyone's ever heard that term before, but like, if dark matter is axions, then it should produce this kind of signal that we'd observe in this kind of way. But yeah, so I've never studied it directly, but so I've heard some of these theories that people have.
Yeah, thanks. Yeah, man.
Oh, by
I
the
love
way,
the talk. Oh, go ahead,
I'm
Ron.
curious to know something. Am I being heard?
Yes.
I'm just curious to know, from your perspective in astrophysics. Um, I mean, I know you people in the lab, people tend to be isolated, focusing on their particular domains. But as a matter of general interest, since we all live on this planet, and there's been a lot of discussion about whether we are actually on a flat Earth or a round Earth, I just wondered, can you cast any light on that shadow in our thinking?
You mean like if the Earth is round or flat?
Right, because there's still a lot of discussion on that matter, and someone like you doing your kind of analytical work, I'm sure you've come to some sane conclusions concerning that one. I'm just curious to know what your opinion is.
So I'm pretty sure. So I'm fairly certain the Earth is round. It's kind of interesting that you asked because there was a point in time where I was like, so one, I'm biased. Like I've always like thought the Earth is round. I've never thought that there would be anything that like would make me not think it was wrong. But that was very interesting at some point in like the arguments that a lot of the flat Earth people had. In particular, just because like there's a community out there, so they must believe it for some reason. So I just wanted to know like what's their reasoning behind it.
Well, there's a highly challenging community, and I think there are even some people at Oxford who support. There's a group at Oxford who I was flabbergasted. They actually support the flat Earth idea. So, this is why I'm curious to hear your perspective.
I don't know about that group, but so I've heard some of the flat Earth arguments. It's like a lot of them don't really hold water. I mean, there's a lot of tests that you can do to see if the Earth is round on like basically with not too much equipment. Like there's predictions you can make if you do the math. Like, so my experience has been that whenever I look at a lot of the arguments that the flat Earth people make, they usually just like is like they get the math wrong and they get the weird results. And because they get the math wrong, they sort of like don't see what they think they should be seeing. But like if you just do the math correctly, you should actually see that the Earth being round makes a lot of accurate predictions, and it just matches observations. But that's been my experience. Um, I haven't met I actually haven't really met any people in flat Earth who uh who buy into flat Earth personally. I've wanted to meet someone before just to kind of pick their brain about it. But I've never met anyone like that. You have to also ask a question about like if how scientists, whether they're isolated or not. It kind of depends on the field and what kind of science you do. The kind of science I do is pretty connected. I mentioned before that I'm in a collaboration with like 300 people. We have like conferences and symposiums and talks every day. It's a lot of communication. Like the whole point of science is to communicate. Like if you have an idea in science and you don't communicate it, you're kind of there's no point. The whole point is to kind of get disseminate information, true information, I guess. So I tend to be my experience with science is that I tend to be very interconnected with other sciences. Yep. Yes, Javon.
Yeah, I was just mentioning that the Google Blitz is like the idea that if you put enough energy within a specific volume of space, you would basically create a black hole. So, a small black hole. So,
Oh yeah, I see. That is true. Because like basically the requirement for a black hole like is just that you need enough energy in a small enough space for there to be a black hole. So I guess the idea is that like the LHC is sort of producing energy in a small enough density that the black hole could potentially be produced. Is that what the idea is? I'm asking. I don't really know. I haven't heard of this.
I think it's theoretical though.
Okay.
Ethan had as a question.
That was me?
Yeah, you can ask a question.
Okay, great. Yeah, I love the talk, Dominic. It was great to hear about the amazing research taking place. I had two questions. One is I was wondering, besides the temporal alignment, having to stitch up all of the bits of the image taken at different points in time, I was wondering what other image processing challenges were involved in getting to the final image. I know you mentioned that there are many possibilities for what the final image could have looked like. So I was just curious as to some of the finer details that and challenges particularly that would have been involved in getting to that final image. If you can explain it in simple terms for the likes of us. And then the other question I had, I was just wondering if you could tell us a little bit more about what your research is like what you're concerned with for your PhD. That would be interesting.
Yeah, so there's all sorts of challenges, especially when the collaboration is this big. Speaking of actually like the speaking of the on the topic of flat Earth, this aperture synthesis technique that I mentioned earlier wouldn't even work if the Earth was flat. It sort of works because the Earth is round. Because
Right.
when you rotate a sphere and project it, it looks different. And because the Earth is round, you can actually look at the data and see, oh, this telescope is being blocked by the Earth when it's looking at the source. But
Right.
yeah, so one of the aspects that's kind of hard about this is like sometimes like things just sometimes weird things happen at each of these sites. Like a fun example is like the weather. One of the hard things is the weather, right? We're all looking at the same thing. You can't control the weather. If the weather could just go bad at the site, and it just means that that telescope can't observe during that time. When the weather is being bad, and the thing about VLBI is that the power increases factorially with the number of sites you add, which also means it decreases factorially with the number of sites you add. So you sort of gain a lot for adding a single site, and you lose a lot for losing a site. So the weather can be like pretty bad, pretty hard. During the most recent campaign, for example, like they have a telescope at GLT now, and it's someone's job like when it's snowing to go and take a big broom and just like remove the snow from the telescope. Another thing that I'm gonna tell mostly stories from GLT just because a lot of people in our local group recently went there. GLT's in Greenland. They're polar bears. Polar bears are kind of dangerous. They can appear during observation, so then you have to shut everything down because you don't want anyone being eaten by a polar bear. Um, there's something that happened in the last campaign. So we have a telescope in Mexico, and we had some scientists that were going up. So it's on a big mountain, and the scientists are like driving up, carrying up a big instrument. I don't remember exactly what it was they were carrying up, and they got stopped by the cartel. because the cartel thought they were like a rival cartel trying to steal oil or something, and they like held them up at gunpoint. So that had to like that stopped observations. So all sorts of like wacky stuff happens.
Wow.
And that's just with like when the observations are running. Like other weird things can happen. Like sometimes, so we have to fly the data on hard drives to the correlators and plug them in, and then correlate the data. And it's a lot of data, so it takes months to correlate. Sometimes like sometimes someone just makes a mistake in the code, and like we sort of realize this like months down the line, and we have to rerun it. Sometimes and like you'll see, luckily like a lot of this stuff has theory behind it, so you can make predictions, and if things don't line up, it kind of tells you, oh, something is probably wrong here, we should check to see if something is working here or not. um so that kind of helps sometimes, but on other times you don't know. Like there's a situation recently where I don't know if I'm allowed to say this. So it's not that big of a deal. Like we have these, okay, we have these, yeah. Oh, I guess before I get there, so we have this collaboration. There are these telescopes. It costs lots of money to run things. So lots of them are kind of uh they care about their institutions getting the results up first. So the data is always public. Like we have to make the data public. But of course, because the telescopes are taking the data, they care if the scientists at their sites get to see the data first. So there's always this like rush for like they're like you're the senior people in charge of like you have to get the results out now, and then we're like it's science, like you can't just like put stuff out. You have to like analyze it. So like even if you want to just put stuff out, the data is gonna be public, so like other people can look at it and see if there's anything weird going on. So there's always this like especially whenever like a release is happening, there's sometimes this like crunch time that you have to do where you're working like a lot of hours in order to like finish the work and get the plots done and the papers done. I recently worked on the 2019 data release, and we went through some rounds of that crunch time. There's all sorts of things, like all sorts of like there's internal rivalries that pop up. Like people want their data analysis technique to be the one that we use in the collaboration, but then like you have like 10 different people independently coming up with 10 different techniques that work in different ways, and like how do you know which one's the one you want to pick? Stuff like that. I could probably go on like forever about like weird things that weird difficulties. There's like things on the social aspect, there's things on the technical aspect.
Right.
Yeah.
There was the second part of his question about your PhD research.
Oh yeah, so I'm a theorist. I was originally studying like stuff related to black hole thermodynamics and black hole information paradox. I got more interested in astrophysical black holes just because, you take data, so you can actually just immediately do theory. So I've been mostly studying gravitational lensing recently. The most recent paper I put out was sort of related to like Pokemon Go. You ever play Pokemon Go?
Yeah, for like a day.
Yeah, so Pokemon Go has this this AR feature where like it's like you take a it's like it uses your camera and it puts a Pokemon like up. It's like in the like background, like somehow it knows a 3D structure of the space you're in from just the picture. And that's just because like, there's certain things we know is true. Like for example, I mentioned that, space is cursed, so light doesn't really travel in straight lines, but it approximately does. So you can like basically like calculate things in small spaces as if light travels in straight lines. So you can do these calculations. You can figure out from 2D images what the 3D structure must be like. So that's how like those things work. And I was essentially doing a similar thing, but for the EHC images that we're looking at. So like if you take an image, can you figure out what the 3D structure of it is? Of course, that question is not well posed, so it's really more of a statistical question. You can say, what's the probability that the 3D space looks this way? And that was the most recent project I did. Like I sort of like made a model that generates the 3D structure and assign probabilities to those 3D structures in order to make measurements for the image. So like the mass, the spin, how fast the accretion fluid is moving around the black hole, and so on. A project that I'm working on now that I need to finish up really quickly is there's various theoretical formalisms that exists for you doing calculations. So I mentioned weak lensing, for example. So this is like a common calculation one would have to do as a physicist, depending on the sort of experiment you're interested in, where things sort of act within what's called a weak gravitational lensing regime. And there's like a sort of formalism and technique that you do to do that calculation. I recently came up with another technique that's like the weak magnification regime of images, and I'm publishing a paper on that. So that's another thing I'm working on. In the past, I've worked on like these calculations. So you mentioned this thing about storing information on black holes. I worked on this calculation for like how much information can you store on a black hole of this type and stuff like that.
Awesome. Thanks.
All right.
Yeah.
Any further questions?
Let's say one last question I'd like to ask. What you guys did a great job. What's next? Are you still on the same team? Are they planning any other targets?
Oh yeah, so there's tons of other targets. The two targets I talked about are just the main targets. Because those are the two targets that they're just the two largest looking black holes in the sky, so they're just the easiest ones to take pictures of. The HC takes pictures of other sources too, but they're not high enough resolution for you to actually see the black hole in the center, but you can see sort of the effect on the environment around it. What's next is that the HC is still adding more sites. So what that will do is that it will slowly increase the resolution of our telescope. It'll slowly increase the dynamic range of our camera, essentially. So we'll be able to see um harder to see features. There's like a space mission being planned that might be launched within the next 10 years or so. So we're planning to put a satellite in space so that we could do VLBI. And if we put a satellite in space, remember, large wavelengths correspond to small scale features. So that should allow us to see even that should allow us to see smaller black holes in the sky. So hopefully be able to have more shadow images. And two, that will allow us to see higher resolution images of the black holes that we already have. There's also like certain things that results that we have that I can't talk about, unfortunately. But just as a hint, I mentioned there's this jet thing that about the black hole, and that we think that the jets are being tossed up by the black hole. Oh wait, this is being recorded. Um,
Yeah.
Okay, I will not say anymore.
Super.
No more.
Yes, super secret results. Yeah.
Yeah.
So yeah. Thanks for the presentation. It was very informative. I learned a lot. I didn't know you were doing probabilistic measurements for the image, because I thought it was just like a direct image, if you're honest what I tried to say. But yeah.
Yeah,
But
and
yeah.
yeah, and I was gonna say if anyone's interested, like I have a website with like various physics apps and applets, and I write blog posts that explains physics
Yeah, I
applets
scanned the
and stuff.
QR code. I think I took a picture of it. Yeah, I took a is that the thing where you look if your work, how much you do work by a black hole?
Yeah.
Yeah, scan the QR code. Like I'll post that in the WhatsApp group so anybody can check it out.
Yeah, and I'd love to participate more in this. Hope maybe when I'm in Jamaica next time, I'd be around the next time you're doing
Yeah,
observation.
definitely. I think Nathan is in US. I'm not sure if he's close to me, but Nathan is also in US, but he's studying what he's studying
I'm engineering. I'm doing engineering.
hmm?
I'm doing engineering. So I
Engineering.
volunteer with the astronomy club, but I'm not actively studying astronomy right now.
Okay. We have a lot of engineers that work at the HT too. Like it's a huge collaboration. All
Mhm,
sorts of people.
mhm.
Where are you in North? What state are you? You hearing me?
For me
No,
or
Dominic.
Dominic?
Oh,
Yeah,
I'm in
Dominic.
Massachusetts.
Right, up north.
Yeah, I'm in Boston.
Did you get to see the lights?
I did not. I went to bed early that night. And when I woke up, I saw people posting pictures, and like, I wish I did not go to bed early.
Missed out.
Yeah, I was very sad. That's
Yeah.
what they get. That they say the early bird catches the worm, but in this case, it did not.
I actually caught it on my camera in Jamaica.
Really,
Yeah.
I'm jealous.
Yeah. So I can share it with you. Yeah, I'll share it with you.
Okay.
But otherwise, I don't know. You say you want to be more involved, so we have a WhatsApp group. I think we should start live streaming. I think Dennison has more experience with that. He can help us out. We can live stream when we have meetings, and so other people who are remote can be more involved in the club activities as well.
Yeah, and if I actually haven't done, so I'm more of a physicist, so I actually don't really know that much astronomy, but I work with astronomers, so if you want me to get information about like tips and tricks and
Yeah, that would be
for
great.
astronomy, let me know. Yeah.
Yeah, that was great. So I'll communicate with you. So I'm the one you've been communicating with
Okay.
via the Instagram. So yeah, we can talk. So if there is nothing else, we can close the meeting. Anybody else have any final questions or comments or thoughts?
Yes, I just wondered whether Dominic is on Facebook. I have a Facebook site. It was established with the help of the Guild, UWI Guild. It's called the UWI Mona Club, and it'd be nice if he could do a post there. It's intended for the young people. Also, he could post at my site on Facebook. We have all sorts of visitors coming in, even some ETs like the Raelians visit. So I think his kind of posts, would be most welcome. I'm on Facebook, Lloyd Gordon. You can find me. I'm the one from the British Museum because I think there are about 25 Lloyd Gordons, but I'm the only one who actually did my research there at the British Museum. So
I
my
see.
picture is quite distinct.
Okay.
Yeah, but I'm not sure Dominic is interested in the tall white aliens.
No, he doesn't have to go that far. I mean, but he can post because some members, like Patrick Lewis of the AAJ, some of the older members of the AAJ, they actually come to my site. It's just that you now have a lot of new people in the AAJ, but some of the older ones, I still see them popping up at my site. Plus, I'm interested in his line of things, so I'm very much interested in his posts, his kind of posts. And also,
Yeah,
as I said,
it's kind of
the
interesting because
guild, the guild thing, because UWI Guild, did help to set up the UWI Mona Club, but I don't see that it's much used by UWI, although I see other people posting there sometimes.
yeah, I was gonna say I do have a Facebook, but I rarely use it. I mostly use like Instagram. So I'm kind of bad with social media. I've been trying to learn. Like a big thing nowadays, especially as like academic, is that you have to know how to use social media. So I've been trying to like use Instagram and Twitter more. I have it's mostly just because that those seem to be the platforms a lot of people use nowadays.
Yeah, I'm also on X. Well, it's now X,
Oh yeah, sorry.
and Instagram. Even Elon Musk visits my site. I noticed. Awesome.
You have to be careful. There's a lot of parody accounts. Elon Musk on the
No,
site.
this is a real one. This is the
But
South African one.
For the AAJ, we have Instagram and there is a Facebook, but I'm not. I don't think we've been updating that for a while now. I posted on the X for the AAJ recently. So I guess that could be considered active as well.
Okay, I look out for the
apart from
AAJ.
that, we have a WhatsApp group if you want to join that.
I'm in the WhatsApp group. I'm in the WhatsApp.
Yeah. No, I'm talking about Dominic.
Oh, okay.
Yeah, you could invite
He
me
wants
to the
to join
WhatsApp
that.
group.
Oh, okay, all right. I'll send you that as well. What else? Yeah, so we can do live streaming. Dennison can.
Yes, man. And you know what, Dominic, and Javon, make it happen. We'd love to have you come and talk more informally about your career choice, man. We really want to get a lot more kids into the STEM field, you know. And I think your story is probably going to be great encouragement to them to see a path through to where you're at. You know what I mean? So please, you know, if you can, you know, spare the time and give a, you know, again, a more informal talk, just, you know, get a sense of, you know, what inspired you, how you chose your career path, etc., and, you know, challenges along the way, and what you would recommend for any other child, you know, a young person who is thinking of heading to STEM and to, you know, fields in research and, you know, such as what you're doing there. Yeah.
Yeah, I had a very like non-traditional like path here too, so I could definitely talk about it. I was at UE for a year actually. Some of the best math teachers I had were at UE. Actually, um, I
Yeah.
learned probability at UE.
Yeah. So any
Did you have
final thoughts?
St. Elmo White? Or did St. Elmo White make any inputs in you?
I'm not sure. The name doesn't ring a bell. So what the name is? So oh, the names are so the two math. There were three math people I remember. Samuels, I think was his
Okay.
name. He had big hair and he always wore black.
Always all black. Yep.
The
Okay.
Italian man Davide Batic, I think was it.
Batik, Dr. Batik, yes.
Yeah, and there was a Russian lady.
Dr. Panakala.
No, no, I
Not
think
Panakala?
I don't think so. It was a Russian lady. But is it Pinakla a Russian lady? I don't
Panakala?
remember.
Yeah, I think she's Russian. I think she's Russian.
Maybe it was her, but the name doesn't ring a bell. But the three people I remember at UE learning math from was I think his name was Samuels Batica. And I don't remember the name of the Russian lady, unfortunately.
Yeah. Yeah, it was a long time ago. You said
Yeah,
it was high school 2013, so it was what 2013 you were at UE for a year, 2014. Perfect.
yeah.
Yeah. So all right. Trisha or Dominic or Shakira,
Yeah.
you want to say anything?
Hi, I'm Tricia. Technically speaking, I'm supposed to be co-hosting this meeting, but unfortunately, I'm at work, so I really only managed to listen into parts of it. But the parts that I got were very interesting, very informative, and I'm really glad that you came and gave a presentation. And I would really love if you would be able to come and give another one on another topic.
Yeah.
Oh yeah, definitely. I could talk about. I technically know more physics than I do astronomy, but I could like do another topic. Like it's sort of easy for me to talk about black holes because that's just what I study. But there are other aspects of yeah, like there's things like galactic formation stuff that maybe I could try and find information about. I could also talk about career things like how one becomes a scientist maybe. Like even if you don't want to be a scientist,
Yeah, that could be a
um
very good thing.
yeah,
Very
because
good.
when I was going to graduate school, I didn't know I was going to get into graduate school. So I actually applied for like software engineering jobs and stuff like that, and I was able to get those jobs. So like, a lot of these skills are transferable.
Okay.
So I could talk about stuff like that, like what sort of things I learned, and what were useful for the job market and things like that.
Yeah. Yeah. So we'll talk. I guess we can close off now. I guess you're probably tired and everybody is probably tired as well because I guess you're an hour ahead of us here.
Yeah, it's 10 p.m. here.
Yeah. All right. So thanks again, and bye everyone. Thanks everyone for coming and staying with us till the end.
Okay, good night, everyone.
Have a good night.
Night, night.
Many thanks for
Night,
having us all.
everybody. Night, night.
Good night.
Bye.